Okay, now it's been recorded. But listen, people, as I mentioned before, this is not a lecture and a conversation. If you wanted it to be just a lecture, I could have posted the answers. I posted myself on our videos. Watch it. You went through all the trouble to get Blackboard covered so we can interact. So I need some conversation here. How many persons attempted the question? Nobody. Okay, Rachel. Wonderful, Rachel. So Rachel, how did you approach this question? Whether you attempted or you tried, whatever the word is, I just need to know how many persons looked at the question. Yes, Rachel. Please turn on your mics. Feel free to jump in, anybody. Your mic is not working, Rachel. Okay, so we have C6H10. How many global equivalents is that? There are many combinations that could be. Okay, understood, Rachel. Background noise, I get it. So if we have C6H10, what are the possible functional groups that could be? No, it would be an alkane at all. An alkane would be C6H14, very just an alkyne. It could also have been an alkene, which is cyclic, or it could have also been an alkene or a structure that has double bonds present. So there are a number of combinations. But then the next step is to look at what we're trying to make, and that is a ketone. And then you'd have learned a number of syntheses for ketones. So based on what you'd have been taught for ketones, you'd have learned that we can make ketones from alkynes. So yes, A will be an alkyne. So since molecular formula is C6H10, as I mentioned before, it means it will have double equivalence. It could mean you have one alkyne present or two alkenes, an alkene in the ring. But you'd have learned that ketones can be synthesized from the hydration of alkynes. Great. So we have now figured out that the alkyne would be A. So the structure of the alkyne, given the ketone that we are forming, where in the chain would we find our bond present, the triple bond present? If we're trying to make 4-methyl-2-pentanone, one alkyne, where would we find the triple bond? Between which carbons? At the end? Okay. So yes, so you have a terminal carbon. So correct, between 1 and 2. So here we have the alkene. Let me put that on the pointer. Here we have the alkyne, sorry, that would give us the ketone that is shown. So the double bond between carbons 1 and 2, the terminal alkyne, and so this would be the structure of A. How many persons got it correct? How many persons had the correct structure? Okay, one person. Yes, Rachel, she's in her hand. Wonderful. Okay. So for B, we're trying to make structure B, and we're using zinc and mercury, which is called zinc amalgam, and it is under acidic conditions. What kind of reaction is this? It's a named reaction. What's happening to the ketone when we react it with zinc, amalgam, and HCl? Very good, Clemmensen reduction. And if we have a Clemmensen reduction, what are we forming for B? Nope, it's an alcohol. A Clemmensen reduction doesn't form an alcohol, an alkane. So you'd have learned that the Clemmensen reduction and the Wolff-Kishner reduction, they both convert a ketone to an alkane. So B would be an alkane. So ketones are reduced to alkanes when reacted with zinc and mercury. We call zinc amalgam in the presence of an acid, normally HCl. And this is a Clemmensen reduction. The Wolff-Kishner reduction would have used hydrazine in the presence of a base, would also give the same product, B. So what we have is an alkane that has been formed. It also asks you to indicate the reagent to convert A to the ketone, and that is already shown. So it's a hydration reaction, and so normally what we use is sulfuric acid in the presence of mercury sulfate or mercury salt and water. Any questions so far? Are we clear so far? People talk to me now. Okay, all right, great. So it's pretty easy. The other part of the question, I think I may have skipped a slide. Okay, well, the other part has to do with the reagent. The third part of the question now, you're told that 4-methyl-2-pentanone could also be prepared from 2-chloro-4-methylpentane. And you're asked to use 2 steps. And you're asked to write equations to show how this transformation could occur. So we are starting out with our 2-chloro-4-methylpentane. And the first thing that we would do is convert the alkyl halide to an alcohol. What kind of reaction is occurring in step 1? Anybody? Very good. Nucleophilic substitution reaction. And even though I didn't ask you, do you think it's SN1 or SN2? And why? Why did you say SN2, Nadisha? Why SN2? Because the substrate is big. But if you think about SN2, remember that for SN2, it normally goes through a pentacoordinate structure. So, right, so secondary alkyl halides and primary alkyl halides, well, in particular, primary alkyl halides normally undergo SN2 and tertiary undergo SN1. Secondary could go either way. So it would depend on other factors that will determine whether the secondary alkyl halide goes by SN2 or SN1. Or the condition that would favor SN2 for a secondary alkyl halide. We're revising. No heat. Heat will give us heat is for elimination reaction. But correct, Justin, a strong nucleophile and a very good at polar aprotic solvent. So do you think the hydroxide has a very strong nucleophile here? Yes, it is. So if you wanted to favor SN2, you would have to use polar aprotic solvents such as very good. Great. So we first form the alcohol, and then the second step, we have the oxidation of the alcohol to give the corresponding ketone. How many persons got that correct? Okay. Any questions so far? Are we all clear? Okay. The other part of the question asks to give the reaction mechanism for the formation of 4-methyl-2-pentanone from compound A. So we are going to be converting the alkyne to the ketone. So the hydration reaction, and note that the very first step is the protonation of the triple bond. And notice that, as I mentioned here, that the reaction obeys Markovnikov's rule, and so the proton will go on the carbon that has the least number of hydrogens, or the most hydrogens, sorry, to create a more stable carbocation. So we are forming a more stable carbocation. So we have the plus charge on the carbon number 2. Water now comes in as a nucleophile, and we're going to end up forming what we call an enol. So notice that this occurs in steps, because when the water adds to the carbon, the oxygen still has the 2 protons attached. And so we have to use another molecule of water to come in to remove that extra proton. Are we following? So the alkyne acts as a nucleophile, picks up the electrophile, which is a proton. It obeys Markovnikov's rule. And so the carbon that has the most hydrogen receives the proton, which makes carbon number 2 the carbocation. Then we have addition of water, and we have oxygen here being positively charged because of an extra proton attached. The molecule of water comes in and removes the proton. So at the end of the reaction, we have formed an enol. So how do we convert the enol to the ketone? Any volunteers to the whiteboard? So the first step is the formation of the enol. But under acidic conditions, very good tautomerization. Would you like to do it on the board? Anybody would like to try on the board? I wish this was live so I can pick on people. Nobody? All right, if you want to go to the board, could you walk me through it? What will happen? What's the first step? Nobody's mic is working? You people are killing me here. Okay. Passenger? Yes, go ahead. Thank you.
All right, come from the double bond. Electrons are removed from the double bond, and
Yes.
then the bond between the O and the H, right there, in the hydroxyl group, those 2 electrons go to to the
Yes.
carbon to form that double bond.
Okay.
So you
Okay,
have a double
wonderful.
bond
So the electron double
forming.
bond, what will they be picking up?
What would be the what? Sorry, miss?
Correct.
You-
Very good.
You'd
The
have the
question I'm
carbon
asking,
group.
you said that the electron, right. But the first thing
Yeah.
that you said was that the double bond would pick up, will electrons will double bond to do what? What will double bond
Mm,
react with?
would it react with
What do you have
the
in the reaction right now? The hydrogen or
what?
the acid, the proton. So what you have there is water which is protonated. You have an extra proton attached to the water. You have H3O plus.
Okay.
Right. So what happens is that the proton is going to react with the double bond. Very good.
Okay.
Thank you.
Thanks.
So here we are showing how the tautomeratin occurs. So the double bond is going to attack the proton from the acid. Yes, Justin. I
Can
did
you
not
go back?
accept because hydrogen is different from a proton.
Okay. Well, my question is slide for 7 seconds.
No problem. Yeah, what's the question you have for that slide?
No, I was just writing.
Okay, all right. So the first step is the enol formation. Under acidic condition, the enol will not stay because once the enol is formed, we'll have a catamerization that occurs in presence of an acid. And so what will happen is that the double bond is going to pick up the proton and it obeys Markov-Nichols rule. So the proton will add to the carbon that already has two hydrogens. The carbon will now become deficient, but we don't form a carbocation. But you can tell me why it's not
Because
formed?
it's concerted.
It's concerted.
Because
Why?
because
Because
as the
in the
double.
first step, yes, go ahead.
Well, if you're gonna answer it, then
No, you were going to say something. Let me hear what you were going to say. It says concerted, and
oh,
I asked you, why is it concerted?
oh, when the double bond breaks, when the double
Mm-hmm.
bond between the two carbons breaks, the double bond between the
Yeah,
carbon and the oxygen is forming at the same time.
but why?
Stability, I guess.
Okay, I'll give you that. I'll give you that. What is directly beside the carbon that becomes positive?
Um, OH
An oxygen. And an oxygen has how many lone pair electrons?
2.
Two. So as the carbon becomes positive, which is next door to an atom that has four electrons, it will quickly go in to quench a positive charge.
Oh,
So that's why you don't form a carbocation like what you see here. It's all happening at the same time because as the positive charge is formed here, the lone pair electron from the oxygen immediately goes in to quench the positive charge.
okay.
So it happens at the same time. So you're correct. A concentrated reaction is because of the proximity of the electron donating group to the carbocation. It all happen at the same time.
Could you see
So as, pardon
tautomization?
me,
If you're forming a ketone, I was wondering if it's like similar to reduction, but like
it's not called a reduction because you're not really adding a proton, you're rearranging the molecule. The same proton that leaves the enol goes to the methyl group. So you're not adding anything new to the structure. If you notice, basically we are rearranging the structure.
okay,
Do you follow?
yeah,
Ketone and your enol, nothing is added or subtracted. You
You
have
just
moved
moved the
the
double bond.
proton from, very good. So you have moved the proton from the OH to the methyl group or the methine, and your double bond is now moved to the oxygen, occurring in the presence of an acid.
Okay, thank you.
So it's not really called a reduction, it's called a tautomerization. All right. So as the double bond picks up the proton from the acid, as you mentioned, a carbon will come deficient. And so the lone pair on the oxygen will just go in and have it's a reaction occur at the same time, it's concerted. And so we end up with a ketone which is protonated. And then the next step is to remove that extra proton. And we lose that using water and we end up with our ketone. So polymerization is a reaction of an acid, and so we are changing the enol to the ketone. All right, good. Let's move on quickly. So part C, again, the past paper question. You're given a sequence below and you're asked to identify compounds A and reagents B and C, and then a mechanism to convert the cyclohexanone to A. So the first step, what kind of reagent is converting the cyclohexanone to A? I've given the answer. It's a Grignard reagent. And we know that Grignards will react with the ketone to give a tertiary alcohol. So you're asked to give the reaction mechanism and you're asked to identify reagents B and C. So after A is formed, the tertiary alcohol, the reaction from a presence of an acid will give us an alkene, and then the alkene reacts with B to give us a dicarbonyl compound. What kind of reaction is occurring in B?
Oxidative cleavage.
Very good, oxidative cleavage. And notice that we are forming aldehyde and a ketone. So which reagent would you use for B? Anybody else? Osmolysis. But we have two types of osmolysis. We have osmolysis with zinc and osmolysis with hydrogen peroxide. Which of them will give the aldehyde? Yeah, the zinc one, correct. So when we do osmolysis followed by reductive workup using zinc and acid, we get an aldehyde. But if we use ozone followed by peroxide, we would end up with, so for B, we would get reduced ozone followed by zinc. Let's look at the mechanism first, this one is A. So remember, always a Grignard reagent, and the Grignard reagent is polarized, which makes the ethyl group negative and the magnesium positive. So first what happens is that the Grignard, I repeat, are you hearing better now? Oh wow, okay. Are you hearing clear? No? Any better? Yes, let me turn off the net. Okay, are you hearing me now? Are you hearing me? Okay, great. Sorry about that. I have no idea what happened a while ago. All right, so the Grignard acts as a nucleophile, and the ethyl portion of the Grignard is going to attack the carbonyl. And so we have the bond being broken, and we have O minus, and so we have the counter ion of magnesium bromide. Under acidic conditions, we are going to protonate oxygen, and we end up with our alcohol. How many persons have the correct structure for A? Remember, ET stands for CH3, CH2, an ethyl group. Okay, great. Great, Nadisha. Anybody else have the correct structure for A? All right, great. Great, Kelsey. So we have a structure for A, and we are told that A will undergo a dehydration in the presence of an acid to give the alkene shown above. And this alkene, as you mentioned, would undergo oxidative cleavage to give compound C. How will we convert C to the acid shown below? Or how will we use C, sorry, to form the acid shown below? So we have used ozone and zinc to form the aldehyde, and we have a conversion of aldehyde to an acid. Very good. I see oxidation. But would we use PCC? No, we use PCC when we want to convert alcohols to aldehydes, so the reaction does not go all the way to a carboxylic acid. But if we have the aldehyde already, what reagent would we use? So when we have an aldehyde and we want to convert to an acid, which reagent would we use? Yes, very good. We could use potassium permanganate, or we could use acidified potassium dichromate or chromic acid. All of those are good reagents that could be used for the oxidation of the aldehyde to the ketone, to the carboxylic acid. All right, so let us complete our reaction scheme. So to convert our alkene to the aldehyde, we use ozone with zinc, HCl, or acetic acid. And if we want to convert our aldehyde to an acid, we will use chromic acid, we could use acidified permanganate, we could use dichromate, all of those oxidants could be used. All right, let's move on to question 2. So for question 2, you are given a reaction scheme using the same ketone, and you have 3 different reagents, and you're asked to give the products of each of the reaction, and then you're asked to give a mechanism for part C. So the first one, we are using an alcohol in the presence of an acid. Now this reaction is a nucleophilic addition reaction in which the alcohol acts as a nucleophile and attacks the carbon of the carbon delta positive. Can anybody tell me why we need acid for this reaction? Why is acid needed for this reaction? If you look at part B, when we're using a stronger nucleophile, as in a cyanide, no acid was used. Can anyone tell me why an acid is needed? Okay, good. Cassandra, why do we need to protonate? Why is the protonation needed for the second reaction, but for the first? Very good. Oh Lord, I'm so happy you guys are learning. Wonderful. Great, just The nucleophile that we are using is a weak nucleophile, and weaker nucleophiles are required to make the ketone easier to attack. Very good. And in the part C, we will see that actual mechanism, because part C is a similar reaction to part A. Only the difference is that we're using a diol in part C and a methanol in part A. So the first thing that happens is that we are going to add one molecule of the alcohol to the ketone, and we end up with a hemiketal. Now, once there is excess alcohol acid in the reaction, this hemiketal will be further reacted to give the ketal. So we'll have two molecules of the alcohol reacting with the ketone. Now, if you only gave the hemiketal, that would have been fine. Because normally, to show that the reaction will proceed to the ketal, we could have written excess or indicate that there are 2 mole. But if you have just the hemiketal, that's fine. If you move on to the ketal, that's great. Any questions? Okay. Yes, Justin, you have a question? Go ahead.
I was wondering, why does it continue if why does it so when it
Continue.
continues, is it becomes substitution rather than addition?
It becomes substitution again. Correct. You're very good. Yes, you're right. So the first step will be an addition reaction, correct? And the second step, you're replacing the OH with a methoxy group. So the second step will be a substitution reaction. In part C, you'll see the actual mechanism, because I did the mechanism for the diol, and I want to show both, because in this step you are using 2 moles or 2 molecules of the alcohol. In part C, you already have a structure that has 2 OHs, which means you have one structure that already has 2 molecules of OH.
Okay.
The reaction occurs twice. So whereas for this one, the 1 molecule of the methanol is from the hemiketal. If you had 2 molecules, it will move on to the ketal. For the diol, the structure already has 2 molecules of hydroxyl group. And so you will form ketal for the part C. So we look at part C later on. So for part B, we have a strong nucleophile, which is a nitrile. And so this is not going to require acidification the first step. So the first, what happens is that we have the addition of the nitrile group to form a cyanohydrin. How many person had the correct structure for B? Okay, great. All right, so part C now, you're asked to show the mechanism. And as I mentioned before, the same mechanism that would be used for part A, if you're asked to show the mechanism for part A. The first step, we mentioned before that alcohols are weak nucleophiles. And so we have to first protonate the ketone to make the carbon more susceptible to the nucleophile. So the first step is protonation of the oxygen, and that gives us a resonance structure where the positive charge now rests on the carbon. So we are now making the carbon more positive and therefore more susceptible to a weaker nucleophile. The very first step is protonation. Once we have made the carbon positive, it can now undergo attack from the weak nucleophile, which in this case is the diol. So the next step is that we have the diol. So the lone pair of the oxygen act as a nucleophile, and the alcohol will attack the carbon, which is positively charged. When this happens, the oxygen still has the proton attached. And so you have to use another molecule of the alcohol to remove an extra proton. So the first step is the formation of our hemiketal. Now, we still have acid in solution, and we still have another molecule of hydroxyl group attached to the diol that was added. So the reaction can continue to form a ketal. What's the first step in forming the ketal? How do we go from a hemiketal to ketal? Anybody? Anybody? How do we go from hemiketal to ketal? The first step. We have acid. What do you think will happen?
May we go protonate the hemiketal again to create a
Yeah, what
better leaving group.
where? Yeah, what
At
would we
the
protonate? There are 3
You
oxygens there.
alternate the OH and becomes a leaving group
Very
with the
good.
oxygen.
Right.
yeah,
So
the
you
water.
protonate the OH. Right. It becomes a good leaving group as water. And when it leaves as water, what you have formed is a carbocation at that carbon center. So the first thing that we're going to do is we're going to protonate the OH. So protonate the OH. And then we have an excellent leaving group, which is water. And now we have a carbocation. What do you think will happen next? Carbocation,
Nucleophile jumps in.
yeah. So the nucleophile in this case is going to be the oxygen on the Langren hydroxyl group. And so this will come around and attack the carbocation. And so the second part of the reaction mechanism is going to give us a ketal. So we lose water, we have our carbocation, oxygen will come in, lone pairs act the nucleophile to attack the carbocation. So the end of the reaction, what we have is a cyclic ketal. So we haven't lost a proton yet. The molecule of the diol will come in and the extra proton. At the end of the reaction, this is what we get. How many persons have the correct structure? Did we get that far? Nobody got it? You fell asleep. You fell asleep. Okay. Nadisha, okay, great. So because you had an OH present and you had acid in the solution, the reaction wouldn't have stopped the hemiketal. It would have continued because you have another molecule of the OH present. And so the reaction would have ended at the hemiketal, it would have continued to the ketal. Okay? All right, 12 minutes left. Let's try and complete question 3. So for question 3, oh, I had made a change to this. This should actually read the our value slides. I changed this to a carboxylic acid. So this should actually be a carboxylic acid. My apologies. All right, so we have a Grignard reaction, or a reaction that goes via a Grignard, and you're asked to identify the different reagents present. So the first thing that we need to figure out is which functional group is required to form a reagent, a Grignard reagent. How do we form Grignard reagents? Anybody? How do we form Grignard reagent? Excellent, alkyl halide. So we'll first have to figure out now, how do we convert the alcohol to the alkyl halide? And then when we have the alkyl halide, then we can form our green yarn. And then we'll convert our green yarn to our carboxylic acid. So this should be a carboxylic acid. All right. So we have our reaction scheme with our carboxylic acid, and we know that we can form our alkyl halide using HCl. Is there another reagent we could have used to form the alkyl halide apart from HCl? Great. So we could have used, yes, you could have used HBr. Actually, it didn't have to be a chlorine. It could have been a bromide. We could have used PCl5. Excellent. Any other reagent we could have used? Chlorine. Okay, so thionyl chloride is SOCl2. Good. So we first form the alkyl halide, and then we react the alkyl halide with magnesium in dry ether to form the Grignard reagent. Now notice that to form the acid, we're using carbonyl. Normally we're adding a carbonyl, and so we need a structure that has two carbonyls and adds only one carbon to the structure, which means that we have to use carbon dioxide. Now the reaction mechanism is identical to a reaction between a Grignard reagent and a ketone. So basically a carbon dioxide has two carbonyl compounds. The end of the reaction, if you're using a ketone, you'd have found alcohol. But because we have two carbonyls on the carbon dioxide, our product has a carbonyl and an alcohol. So let's go to the mechanism of the reaction. So just like you'd normally do for a ketone or carbonyl, we have CO2, which has two carbonyl groups. The Grignard we know is polarized, and so our magnesium carbon bond, the magnesium is positive, the carbon is negative. So the alkyl group acts as a nucleophile. So we have the electrons going from the carbon to the carbonyl, which is a positive because it's flanked by two oxygens. So as the nucleophile comes in, as we have done for regular ketone, the CO bond is going to break, and we have a ion with the magnesium chloride. That's the first step. Notice only one carbonyl reacts. So your product after the first step would have one carbonyl group remaining, and the other carbonyl group would have been opened to give your oxide. The second step is a protonation, and so we protonate the oxygen and we end up with a carboxylic acid. So the reaction between CO2 and a Grignard is the same mechanism as if you were using a ketone. Have any questions? So we're okay with this mechanism? Yes? No? Is it clear? Should I repeat? Okay, great. All right, so that was it for tutorial number 5. I hope it was helpful for revision. On Thursday when we meet, we are going to be reviewing Wittig reactions and looking at carbonyls as nucleophiles. So we'll complete. Oh, let me repeat. Okay, Basandra, I see your question. The point I was making is that the reactions that we have looked at so far are reactions between Grignards and carbonyl groups, so aldehydes and ketones. So aldehydes will form a secondary alcohol, and ketones will form a tertiary alcohol. CO2 has two carbonyl groups, and so the reaction occurs in the same way as it would with a regular ketone or aldehyde. The only difference is only one carbonyl group reacts and the other carbonyl group remains unreacted. So at the end of the reaction, you retain one of the carbonyl groups and add a hydroxyl group, which is why at the end of this reaction, you will form a carboxylic acid and not an alcohol as you'd have formed for ketone aldehydes. Is that clearer? A bit? Okay. A bit doesn't sound clear. What is the question that you have?
Yes, explain the, what's it? You have the, what's it, the Grignard reagent here with the
Yes.
MgCl
Yes. Yes.
attached to the cyclohexane ring.
Yes. Correct.
Uh,
So Grignards can be cyclic and can be acyclic. Correct? Yes.
okay, so you have electrons coming from the bond attacking
Mm-hmm.
the, what's it, the double
The
carbonyl,
carb. Yes. Correct.
the carbon,
Yes.
and then so
So
you
do
have
you
bonds
remember
between
do you
C.
remember the reaction that we did earlier with a regular ketone in the very first question where we had done the ethyl group? You remember that reaction? The same mechanism. Or the difference is that the CO2 now has two carbonyls. Yes, Justin, go ahead.
No, I'll wait. It's just that I
Okay,
had my
I'm
hand
so
up and then it just went down for some reason. So I was just keeping it up and waiting for him to finish speaking.
Oh,
four
okay.
methyl
Okay.
propane. So,
Go ahead. Come to what you were saying, Bassandra, and Justin, you can speak. Right. So I was saying that the CO2 is basically a diketone or a dicarbonyl. What it basically is. So it reacts like a regular carbonyl. Only one carbonyl will react. At the end of the reaction, you will still retain one of the carbonyl groups. If you're a ketone or an aldehyde, at the end of the reaction, you'd have whatever a methyl group here or a hydrogen here if you had used an aldehyde or a ketone. But because it's a dicarbonyl, only one of the carbonyl will react. At the end of the reaction, you retain the other carbonyl. So what we have formed is a carboxylic acid. Any clearer? All right, Justin, you have a question?
Yeah. Question: Is it possible, like if you have Grignard reagent in like solution, I guess,
Mm-hmm.
and then you put in carbon dioxide, after it forms that carboxylic acid, there's
Mm-hmm.
technically another ketone group present. So can a Grignard reagent attach itself to that carboxylic acid?
No, because this ketone is no longer the kind of ketones that will be attacked by Grignard. It is now flanked by the oxygen. So there is a resonance.
Like stable
And so
zones?
carboxylic acids, yes, so carboxylic acids don't normally undergo Grignard reactions. And you should tell me why. If I add this acid to a Grignard, what will I form? Excellent exam question.
Hmm?
What would happen instead?
Yeah, acid too.
If I add an acid to a Grignard, what happens instead? Excellent exam question.
Oh, I didn't sign up to answer this
When
question.
Grignard react with a proton source, what is formed? Very good, Nadisha, at alkane. Excellent. I am so proud of you guys. Excellent, yeah.
So when
So
that
under acidic conditions, right. So what happens is that remember the easiest bond to break is a plus minus, it's a protonation. Once in solution here, this acid will now deprotonate. So if you have extra Grignard in the reaction, it will actually form the alkane. So it will form cyclohexane. It will protonate the grignard to form a cyclohexane if there's extra grignard in the reaction.
So what would happen is it forms the carboxylic acid, and then the remaining Grignard reagent,
Mm-hmm.
MgCl on the cyclohexane, the
Mm-hmm.
remaining of those would be
Mm-hmm.
protonated.
Yes. So if there's extra grignard in the reaction, the grignard reagent will be protonated on alkane. So in
So
grignard reaction, it proton source, it form alkane.
okay, would it be possible for it to like form all carboxylic acids, and then immediately after just deprotonate everything back and just result in nothing but cycloalkane?
No, the carboxylic acid will not this will still be in solution. So you'll have the carboxylic anion, O minus, and you have H plus.
Uh-huh.
It will react with this, the grignard, to protonate this grignard to give you cyclohexane.
Oh,
So when grignard react with an acid, yeah, so that this will still be in solution as the
so
counter ion.
you'd still
The
you end up
conjugate base will still be in solution.
okay, so you end up with the acid, conjugate base,
Yes,
and
yes,
a lot of
and some
alcohol.
alkane.
Okay.
Yeah, some alkane, if there's extra grignard reagent present.
Please don't make
Wonderful. I should ask the next group this question to see if they give me a. Okay, great. All right. If there are no more questions, thank you guys for coming on. I really hope that you're revising. And I mentioned before that my office hours are Tuesdays and Thursdays. So Tuesdays from 3 to 5, Thursdays from 10 to 12 on RVLE. Any questions you have, any concerns, feel free to come on and I will see how I can help. Okay? This week you should get some information about your second course test, which will be done online, of course, on RVLE. You will get more information as the week progresses. Okay? Okay, guys. So have a good week. Okay, bye.